What is a moment generating function? Well, by the end of this video, you're going to know. So to start with, we first need to look at what a moment actually is, because what's good is knowing what a moment generating function is if you don't even know what a moment is. So a moment in probability and statistics is the expected value of a random variable to a power, so to the power of n, and typically n is going to be a natural number. So the first moment, the expected value of just x, or x to the 1, is of course the mean. We know it, the mean, the expected value of x. You also could have the expected value of x squared, the expected value of x cubed, etc. All of these are moments, the first moment, the second moment, the third moment, etc. And you have ideas and things like variance, and variance isn't exactly the second moment, but it's quite close. So the variance of a random variable is defined as the expected value of x squared like this, minus the expected value of x in brackets squared like this. So in order to calculate the mean or the variance of a random variable, you might want to derive the moment generating function of that random variable, which is what we're going to talk about. And it's literally a function that is going to spit out the moments, okay? And it's going to involve things like differentiation and all that stuff. We're going to get into it. One more thing we need before we actually say what a moment generating function really is we need to remind ourselves the way to actually calculate the expected value of x, or the expected value of x squared and all of that stuff. So there's two situations. Either your random variable is discrete, in which case the expected value of x will be given by the sum over all of the possible values that your random variable can take, so over x, of x times the probability that the random variable takes that value. Hopefully everyone should be pretty happy with this. The other situation is that x is continuous. And in that case, the expected value of x is given by the integral from minus infinity to infinity of x times the probability density function like this, okay? So this is the expected value of x if it's continuous. Now, what we're going to do is define the moment generating function in terms of this. So what we're going to do is now actually talk about what the moment generating function is, or what is a moment generating function. The moment generating function, and we're going to write it like this. So it's going to be capital M sub capital X of a variable t, okay? And this just means the moment generating function of the random variable x, but it's a function of this new thing that I'm making up called t. So it's not a function of x per se, it's a function of t. That's how we're thinking about it. And it is defined, regardless of whether x is discrete or continuous, it is defined as the expected value of e to the power of t times the random variable x, like this. And now the way that you would actually calculate that does depend on whether x is discrete or continuous, of course, but regardless, it's defined as the expected value of e to the power of tx. Now, before we actually go ahead and say, oh, well, what if x is continuous, or what if it's discrete, and how do you calculate it? I'm going to make a case to you on why we are even doing this, or like why it makes sense to do this, and the benefit of defining it like this, because this might seem really strange. E to the power of some letter t that we've made up times a random variable in the power, it looks crazy. But of course, we can do some really cool stuff with it, and that's what I'm going to show you how to do now. So what we can do here is we can actually use the Maclaurin series, or the Taylor series centered about 0, for e to the tx to rewrite the moment generating function as the expected value of the following. So 1 plus tx plus t squared over 2 times x squared plus, dot, dot, dot. And in general, the kind of nth term of this is t to the n over n factorial times x to the power of n, like that, okay? And of course, that's going to keep going forever because it is the Maclaurin series, but this is what we can expand it to. So we're using the Maclaurin series to do this. Now, what's the benefit of that? Well, we can use the linearity of expectation to rewrite it once again. It's the expected value of 1 plus t times the expected value of x plus t squared over 2 times the expected value of x squared, and so on and so forth. And in general, we've got t to the n over n factorial times the expected value of x to the n plus dot dot dot. And again, it goes on absolutely forever because it is an infinite series, it's a power series, but we can do this. T is not a random variable, it is just a real number, and so we are allowed to take it out of the expectation. We're allowed to do this. And again, you're probably wondering, what is the point? What's the big deal with this? This is the cool bit, this is the clever bit. So let's say that I want to find the nth moment of my random variable x. I would like to find the expected value of x. Let's start with an easy one. Let's start with just the expected value of x, okay? So I've got a function. I'm telling you I can make a function, the expected value of e to the tx. I can do a calculation, which I'll show you how to do at the end, and then I can essentially come up with a function in terms of t, and I can manipulate it in some way to generate the expectation of x, or x squared, or x cubed. Let's start with x squared. Looking at this Maclaurin series, this series of expectations, we can think about how would we find the expected value of x, right? So first things first, we can just notice that the moment generating function when t is the number 0 is just the expected value of 1, so it's just the number 1, okay? So this will happen regardless of what your random variable actually is. The moment generating function when t is 0 is always going to be 1. This is the interesting part. If I differentiate the moment generating function, so I differentiate it and I evaluate it at t, looking at this expansion here, what will happen? Well, we can differentiate it term by term. It's really easy. So the expected value of 1 just disappears. And then we've got t times the expected value of x. Remember, we are differentiating it with respect to t because t is the variable. So t disappears and we end up with the expected value of x. And the next term, t squared over 2, is just going to become t times the expected value of x squared. And of course, there's going to be loads of terms. And in general, the nth term, this t to the n over n factorial times the expected value of x squared, this is going to become t to the power of n minus 1. The n is going to come down, kind of cancel out. We're going to be dividing by n minus 1 factorial, and we're still going to have the expected value of x to the n there, and so on and so forth. Now, what you can see is if we evaluate this derivative at 0, so the moment generating function, the derivative of it evaluated at 0, out pops the expected value of x, which is really, really nice. And you might be able to see that if I was to take the second derivative, I will do this one just so you can really see it in action. If I was to take the second derivative of my moment generating function, the same thing will happen. So I'll lose my expected value of x because that is a constant with respect to t, and I'll be left with just the expected value of x squared plus, and then the next term would be t times the expected value of x cubed, and of course it would go on, and in general the nth term now is going to be t to the n minus 2 over n minus 2 factorial times the expected value of x to the n dot dot dot. And I can evaluate this at 0 as well, and you can see that I will get the second moment. So all I've got to do to get the second moment of any random variable is just differentiate the moment generating function twice and then evaluate it at 0, and you can see that all I'll be left with is just the expected value of x squared. So hopefully you can see that I can make a kind of inductive argument to say that in general the nth derivative of my moment generating function evaluated at 0 will just spit out the expected value of x to the power of n. Okay, and this is really the power, no pun intended, this is the power of the moment generating function. It's a function that has this property. Really nice, really cool. Now, if this is still a little bit abstract because we've not actually done an example, then that is okay. I'm going to show you an example right now, and I'm going to show you how to derive the moment generating function, what one might actually look like, and a nice example that's going to get us going. Let's have a look. Okay, so we're going to actually find the moment generating function for a Poisson distributed random variable. So let's say that we have a random variable x and it has a Poisson distribution with a parameter lambda. Let's derive the moment generating function. So guys, remember that the Poisson distribution is a discrete probability distribution. So x is a discrete random variable. That means that, and I'm going to write this down in a different color here, the expected value of just, let's say, x here, we're going to not use the integral because that's for continuous functions. We're going to be using this one. So it's x times the probability that x equals x, like this. And in this case, the Poisson distribution is defined for when x is 0 all the way up to infinity, like this. So this is how you would calculate the expected value of x without a moment generating function. Of course, if you wanted to find the expected value of x squared without the moment generating function, you'd have to work out what this sum is, but instead you would have a squared up here. Okay, and obviously the probability that x is equal to lowercase x, we can fill that in because we're talking about a Poisson distribution. But in general, we don't want to have to do this every time. What if you want to find, a bunch of different moments? Difficult. So let's just write down what the moment generating function is. So the moment generating function, m sub x of t, remember it is defined as the expected value of e to the power of t x, like this. Now this is the sum, because again it's a discrete random variable this time, from x equals 0 to infinity, because this is the sample space of the Poisson distribution. And instead of x, we're using e to the tx. So it's e to the t, and we use a lowercase x when we actually plug it in here. And we're going to multiply this by the probability density function, or the probability mass function of the Poisson distribution. So guys, I've just filled this in. This thing that I've just added here, lambda to the x times e to the minus lambda over x factorial. This is simply the probability the Poisson random variable takes the value little x. Okay, so this is how we're going to calculate the expected value of e to the tx. Now, with a very small amount of rearranging, I've chosen this one because it's quite easy, but with a very small amount of rearranging, we can make a nice closed form expression for this. We don't need the infinite sum. So the first thing we can do is we can just take e to the minus lambda out because it is a constant. So this is e to the minus lambda, and then we can rewrite the sum. And I'm just going to rewrite that because it's a bit messy. There we go. From x equals 0 to infinity. And then what I'm going to do here is I'm going to rewrite e to the tx as e to the t and then to the power of x. So hopefully it makes sense that I can rewrite this, guys, as e to the t times lambda all to the power of x, because I've got my lambda to the x, and this can be rewritten as e to the t to the x, so I can do that. And then of course I can just have this being divided by x factorial. Now this is a slight leap, so I'm going to write this down, but remember guys that e to the power of just x is again, this is just using the Maclaurin series, which we've already used, but it's the sum from, let's say, r equals 0 to infinity of x to the power of r over r factorial. Okay, so can you guys see that actually we have like x is kind of acting like r here, because we've got x equals 0, x factorial x. You guys can see r factorial r. So we have the same kind of form, and instead of x, we're using e to the t times lambda. So hopefully it's not too much of a leap for me to say that this is equal to e to the minus lambda, and this is the Maclaurin series of e to the t lambda. I know that looks a bit crazy, but that's what that is. So I've got e to the minus lambda times e to the power of e to the t times lambda. Okay, I know it's a bit crazy. And then of course we can rewrite this as e to the power of e to the t lambda minus lambda. And this can be rewritten as e to the power of lambda times e to the t minus 1, like that. And so what this here is it is a function. You can see it's a function of t. There's no x in it at all. And this function has the amazing property that if you differentiate it n times and evaluate it at 0, it will give you the expected value of x to the n. That's what it is, because it's the moment generating function. So let me write down what I've just said, because that's it's a lot of information. So the moment generating function of a Poisson random variable, but we're saying that it's the function, the moment generating function is this variable t. This is equal to e to the power of lambda times e to the t minus 1. All we've got to do is differentiate this, and it will start giving us the expected value of x, the expected value of x squared, the expected value of x cubed, just like that. Really nice. So hopefully we all know, just as a side note, because I'm going to kind of prove to you now that this actually works. But guys, remember, for a Poisson random variable, so if x has a Poisson distribution, with a parameter lambda, we know that the expected value of x is just lambda. We already know this. This is just a known fact. Lambda is the mean of the random variable. So if I differentiate my moment generating function once and then evaluate it at 0, I should just get the number lambda. Because the first derivative evaluated at 0 is the expected value of x to the 1. The expected value of x is the mean. So let's just do that and make sure it works. So the derivative of my moment generating function here is, and what are we going to do? Well, we're just going to differentiate it. So what is the derivative of the power here? Well, it's nothing other than lambda times e to the t. And then we rewrite it, e to the lambda e to the t minus 1 like that. So a bit of chain rule, bit of differentiation. You've got to make sure you're pretty happy with that. But this is what we've got here. And if I now evaluate this when t is 0, what do I get? Well, I've got lambda times e to the 0 times e to the lambda times e to the 0 minus 1. And what's this? Well, this is lambda, e to the 0 is 1, and then I've got e to the power of lambda times 1 minus 1. So we can see that this is lambda times e to the 0, which is just lambda, which is, again, exactly what we expected it to be. Okay, cool. Let's do one more. What is the variance of a Poisson random variable? Do we remember? Well, the variance is actually lambda as well. This is just a known fact, I'm telling you. So what we should have is that if we take the second derivative and evaluate it at 0 and plug that into the formula for variance, we should get lambda as well. Okay, so one more quick side note before we actually do that. I'm going to write it here. Remember that the variance of a random variable is the expected value of x squared minus the expected value of x squared, like this. So the second moment minus the first moment squared, like that. Okay, so let's get the second moment and then plug it in and make sure we get lambda as well, and then we can be pretty convinced that it's working. So let's do it. Second derivative. Okay, now we're going to need to use the product rule here because there's two functions timesing together. So this is going to be lambda times, I'm differentiating e to the t now, that's just e to the t again, times e to the lambda times e to the t minus 1. And then I'm going to add, and I'm going to differentiate e to the lambda e to the t minus 1. Okay, mouthful. But I've got lambda e to the t, and then differentiating this. We already know what this function differentiates to. It actually just differentiates to lambda e to the t e to the lambda e to the t minus 1. Okay, again, absolute mouthful, but that is the second derivative. And so let's simplify this. We've got lambda e to the t, e to the lambda e to the t minus 1, plus this is lambda squared e to the 2t e to the lambda e to the t minus 1. Crazy stuff, but there we go. And then let's actually evaluate this when t is 0. So we're going to have lambda times e to the 0 times e to the lambda. This is basically 1 minus 1 here, plus lambda squared e to the 0 e to the, again, this is like 1 minus 1. So we've got lambda times e to the 0 times e to the 0 plus lambda squared times e to the 0 e to the 0. So the second moment of a Poisson distribution is lambda plus lambda squared. Cool. Now remember, that's telling us that this is the expected value of x squared. So it's not equal to the variance. This is the expected value of x squared. So now to get the variance, if we want to do that using our moment generating function, we can remind ourselves again, it's at the top, it's the expected value of x squared minus the expected value of x squared. So it's lambda plus lambda squared minus the expected value of x, the first moment, actually squared. So the first moment, again, it was lambda. We did it. It's up here. And we need to square it. So it's just lambda squared like this. And you guys can see that it's just lambda. And so this is, again, exactly what we expected it to be because it's the variance of a Poisson random variable is lambda, so it works. So that was just one big example, guys, but the real takeaway of what we did today and what the idea of a moment generating function is we've made up this notion of a function that's related to a random variable the expected value of e to the power of tx such that it has this kind of relationship between the moments and the function itself. So the moment generating function, the nth derivative of it, evaluated at 0, will give you the expected value of x to the n. So not only is this a really, really nice way for a lot of quite difficult standard probability distributions, you can do this for anything, the geometric, the binomial, the Poisson, the normal, you can get the moments of all of these different probability distributions using this idea. But not only is it that, but you can actually prove a lot more than that using moment generating functions. There's so much to it. So this is an incredibly important concept in probability and statistics. So 100% make sure you're behind it. But I'm going to do loads of videos in the future deriving the moment generating functions for all sorts of probability distributions and random variables. So stay tuned for that. If you enjoyed the video, subscribe and like if you enjoyed it, and I'll see you in the next one. Cheers.